Yeah. So my name is Anirban, and I'm a PhD student at the Indian Institute of Astrophysics in Bangalore. So today I'll be talking about a single object, which is called the supernova 2011 AA, and we will try to see what is the progenitor which can give rise to such a supernova. So the title of this talk is Can the violent merger of white dwarfs explain the slowest declining type 1a supernova 2011 AA? And I have performed this work with our group at IEA. So we know that we all know what a type 1a supernovae. So they are explosions due to thermonuclear runaway in a degenerate stellar system, mostly of a white dwarf in a binary. And you can look at these excellent reviews for more details. And before going to our work, I'll just briefly tell you about the Thermonuclear Zoo. So the normal one is are those which sort of obeys a decline rate luminosity relation given by Phillips in 1993 and followed in 1999 and other people also. And but there are over 30 and 30 to 40 years, we have observed a lot of thermonuclear objects, and there are some spectroscopically peculiar objects, and some are there which does not obey the Phillips relation. So few so of them, the 91T like luminous objects, which sort of lies here. Then there are 91 BG like cool and subluminous objects, and the FG like superchandra objects with masses exceeding the non-rotating inert white dwarf limit of 1.4 solar mass, the Chandrasekhar limit. Then there is this 1A CSM, which are very bright and has hydrogen in their spectrum. Then there are 2002 CX like fast declining low velocity 1XS. You can see our work on 2020 SCK if you're interested on 1XS. Then there are calcium-rich transients, as we just learned about, 2005E, and there are lesser luminous but slowly declining peculiar objects which are thought to be of thermonuclear origin, the 2002 ES-like objects. So when we are speaking about 1As, we have to sort of include a distance into account. So there is a relation for calculating the extinction from the tail of the color evolution in B minus V from normal 1As around 30 to 90 days, and from which we can calculate the extinction. And from light curve filters like the multi-light curve shape, which was used for calculating distance as well as extinction, and the spectral adaptive light curve template, which consists of a luminosity, then a color, a stretch, and a time of maximum. So this all does not fit a distance as a parameter, but you can use other relations and some other parameters to derive a knowledge on a distance. So so then I discuss about the progenitors on 1As. There are a few progenitors which have been proposed for explaining 1As. The single degenerate scenario in which a carbon oxygen white dwarf accretes matter from a main sequence star. Then another one in which a carbon oxygen white dwarf accretes matter from a red giant or a helium star. The main sequence companion has been proposed to be proposed to produce more supernovae 1As, and which matches the galactic supernovae 1A rate. And then there are double degenerate progenitors in which there is merger of carbon oxygen and carbon oxygen white dwarf through loss of angular momentum and gravitational wave radiation, and there is merger of carbon oxygen or helium white dwarf. And there is another way of in which a double degenerate explosion can happen, in the collision of white dwarfs in a dense stellar system like that of a globular cluster, or collision of white dwarfs due to the presence of a third star in a highly inclined orbit, which induces quasi-Lidov oscillations with high and produces higher eccentricities in the inner binary and causes the white dwarfs to collide. Now, I'll talk about our observations of 2011 AA. So we have observed it with a 2-meter optical IR facility at Ladakh in India. So this is a Ritchie-Christian system with an Altas mount. There are 3 instruments on its Cassegrain focus: the optical imager and spectrograph. Then there is the infrared imager and spectrograph covering a wavelength range of 1 to 2.5 micron. And there is this shell spectrograph with high resolution around 30,000 and 60,000. So 2011 11A observations have been made mostly with in optical with the HFOSC. So here is the identification chart for 11A, which was discovered on February 26, 2011, between this pair of interacting galaxies, PGC 021, 381, and 386. It is the projected distance. It has a projected distance of 6 kiloparsec from the center of UGC 3096. Without taking into account the shape or size of the galaxy. This is just the projected sort of R theta relation. And we have a temporal coverage in photometry for about 120 days and spectroscopic coverage for 70 days. And SWIFT also followed this supernovae from February 11 to April 4. The UV observations has already been published in Brown et al. 2014. I now show you the light curves of 2011 AA. We used a Gaussian process regression to estimate the maximum magnitude, maximum JD and decline rate. The peak magnitude in B band is something around minus 19.3, which is sort of normal for 1As. And but the decline rate is really slow. This is the slowest declining 1A of 0.59 mag. And the secondary maximum is equally bright in the I band. And such slower decline is mostly seen in superchandra objects like 2006 GZ or 2009 DC. But they're really bright, like 2009 DC was around 1 mag brighter than 11 AA, and 2006 GZ was around 0.4 to 0.5 mag brighter. But another peculiar object of which is close to 2011 AA was 1 AY, which is like with a delta M15 of 0.68 and magnitude of minus 19.2. So we performed a quasi-bolometric fit to the UV optical light curve with this analytical radiation diffusion model, which takes into account the deposition from nickel and also gamma ray deposition with this factor. The assumptions in this model are homologous expansion, then no mixing and one zone, and that the radiation pressure dominates the gas pressure. And then we fit the radiation diffusion model with fit the observations with the radiation diffusion code, and we get a nickel mass of 0.75 solar mass, which is sort of normal for 1As, around 0.5 to 0.9 solar mass. And using a constant opacity and an expansion velocity of around 12,000 kilometers per second, we estimate an ejecta mass, which is sort of superchandra, like 1.65 to 2.48 solar mass. So any explosion model we should consider should explain this higher ejecta mass and normal nickel within the ejecta, normal nickel produced within the ejecta. So we considered Monte Carlo fit to the radiation diffusion with which gives us the parameters. The fit parameters are nickel mass, the diffusion time scale, the gamma ray decay time scale, and the time since explosion. Then we show you the color evolution of 2011 AA, which is sort of similar similar as 2012 DN and 9 DC, which are both superchandra objects, classified as both superchandra in the literature. And here I show you the SWIFT UVW1 minus UVV and UVB minus UVV colors. Though the supernova is in blue in the NUV, but the B minus V color shows very little scatter in all these objects. So the superchandra objects are basically near UV blue, and AA also follows a similar trend. Then I show you the spectral evolution for 2011 AA. So it shows presence of a silicon 3 and iron 3, indicating a hot photosphere around minus 10 days since explosion, 10 days since Bmax, I'm sorry. And it shows presence of unburned carbon in the early phase. And we compare this object with a luminous 1991T, a peculiar 2001 AY, a normal 2005 CF, two superchandra objects GZ DC, and a transitional object between normal and superchandra 2013 CV. As we see that the evolution is not very similar to either 2001 AY, which shows sort of broad and a deep feature, which is in the literature it is also called broad line. According to a classification scheme, but this object shows that silicon is co-normal according to some silicon line ratios, and then it is also not very similar to 9DC or GZ according to the velocity evolution. So it's quite separate in a sense of its spectroscopic evolution also. And I show you the evolution of the velocity in terms like from time since B band maximum. So the velocity evolution of silicon after maximum is around 40 kilometers per second per day, which is similar to 2005 CF. But carbon is present at lower velocities compared to silicon, while carbon or unburned elements should be present at velocities which doesn't reach nuclear statistical equilibrium. And the presence of carbon post maximum at lower velocities is indicative of mixed abundance or maybe a line of sight effect. So we consider three possible progenitor scenarios to explain the explosion of 2011 AA. First, we consider the collision of white dwarfs, and then we consider rotating white dwarfs, which can go beyond the Chandrasekhar limit. And finally, we consider the violent merger scenario. So head-on collision of white dwarfs of two different masses of 0.6 solar mass and 0.9 solar mass has been studied in Raskin et al. Which produces around 0.4 solar mass of nickel, but higher mass white dwarfs will definitely produce more nickel mass. But according to 3D simulations done in Roswag et al. With using 2.9 solar mass white dwarfs, they have shown that the ejecta structure is highly stratified with carbon and oxygen present at higher velocities in the outer layers, followed by silicon in the inner layers, and followed by nickel 56 and iron group elements in the innermost layers. There is another simulation done by Kushnir et al. In 2013, which with head-on collisions on 0.64 solar of 2.64 solar mass of white dwarfs. And in this work, they have considered a wide range of masses, like 0.5 to 1 solar mass, which yields a nickel mass in the range of 0.1 to 1. Here also we see that the density structure is quite stratified because the detonation front propagates faster in the higher density region compared to the lower density region. So here also we get a stratified ejectum where carbon or oxygen is present mostly at the outer layers. So again, then we consider the rotating white dwarf. So inert carbon oxygen white dwarf, which is having no rotation, so it should have a 1.4 solar mass limit, which is known as the Chandrasekhar limit. But carbon oxygen white dwarfs having differential rotation can support mass exceeding the Chandrasekhar limit. So according to a simulation done by Fink et al. In 2018, they have calculated models based on 1.6 to 2 solar mass white dwarfs with different angular momentum, and which yields 1.06 to 1.45 solar mass of nickel. The ejecta structure here is also stratified with carbon and oxygen in the outer layers and nickel in the innermost layers. The model produces huge amount of iron group elements of the order of 1.3 solar mass, but a specific model, the accreting white dwarf model, model, which produces around 1 solar mass of nickel, similar to 2011 AA as we derived from our analytical fit, and but it produces a huge amount of IgE and 0.3 solar mass of IMEs, or silicon, magnesium, calcium, and all those. Then we consider the merger of violent merger of two white dwarfs. So this is a three-dimensional simulation done by Packmore et al. In 2012 of two carbon-oxygen white dwarfs, 0.9 and 1.1 solar mass, which has an ejected mass of 1.95 solar mass. And the peak magnitude in B band varies between -19.5 to 18.7 with an angle average value of -19, and the decline rate is sort of between 0.5 and 1.4 with an angle average value of 0.9. It predicts slower evolution of velocity due to the presence of presence of the secondary white dwarf, and also this depends on how intact the secondary is. If the secondary is intact, then it will hardly the ejecta will hardly interact with the secondary, and if the ejecta is more spread, the ejecta and the ejecta or the explosion from the primary will hit that and will cause a velocity plateau. And it predicts mixing of carbon and oxygen in the inner layers, because as the primary gets burned, the ashes of the primary moves apart while the secondary is still burning. But at that time of when the secondary is burning, it has already lower densities. So when the burning is happening, it will at most burn to IMEs, and the middle portion will be dominated mostly by carbon, oxygen, and silicon, while the nickel and iron will be present mostly from the burning of the primary. But it predicts carbon and even oxygen, oxygen and even carbon at the inner layers, in the inner layers. So I show you the uh, spectral comparison of 2011 AA with Fink 2018 WD1 model. The models are taken from the Heidelberg Supernova Model Archive or HESMA database. So as you see, the models are very blue, and also it produces a lot of iron and does not matches the observed properties of observed spectral evolution for 11 AA. And here is, these are all angle average spectrum. I forgot to mention that. And this is the violin merger model where we from Patmore et al. 2012. Here you can see that the near maximum spectrum, though it has a redder, the synthetic spectrum is redder before maximum, but near maximum it predicts the lines quite nicely. This is from Patmore et al. So motivated by this, we performed radiative transfer simulation with a publicly available code called SEDONA. So it is a multidimensional time-dependent radiative transfer code, which uses homologous expansion, Sobolev approximation, and local thermodynamic equilibrium. And all the lines are treated in the expansion opacity formalism, which is defined by Karp et al. In 1977. And the lines are beamed in wavelength. The radioactive energy arises mostly from the decay of 56 nickel. The source function is treated in the two-level atom approximation, where there is a free parameter called epsilon, which controls the probability of absorption. Like epsilon is a probability between 0 and 1. So 1 is that the ejecta is fully absorptive, and the epsilon of 0 means the ejecta is fully scattering. So we have performed all the calculations in this work in one dimension in our IA's high performance computing center. And
about 2 minutes left.
Yes. So we have, so I'll just keep the setup and all and show you the results. So I have used the violent merger density profile with the abundance from the violent merger model in one dimension, averaged over angle. So as you can see that the spectrum is initially very red, and the lines due to iron and magnesium and iron blend here is quite prominent. So in the second model, we increased nickel in the inner layers to sort of see how the model evolves, like how the spectral continuum can be matched. And these are all calculated with epsilon of 1, which is an absorption dominated treatment. And in the third model, we reduced epsilon using the abundance and density same as the second model. In this third model, we have used epsilon of 0.5. So we see there is a slight increase in the bluer region post maximum. And in model 4, which is where we have used an epsilon of 0.3, we see that there is an increase in the bluer region, while there is a sharp drop in the flux in the V band or near B and V band. So we also simulate light curves with this code, and we find that model 1 and 4 are not really matching, while model 2 and 3 sort of matches the color evolution and a light curve in each pass band. But the bolometry is hardly differentiate. We can hardly differentiate between the models, because epsilon is a probability which gives you the redistribution of flux, so it doesn't affect the bolometry. And in a non-LTE calculation by Shane et al. Has shown that the UPVRI, U and B light curves can be more accurately modeled in non-LTE, where there is lesser effect of iron to line blanketing and calcium emission. So here are the four features from the four models. In model 4, we got a delta M15 of 0.59 and minus 19.31, but the light curves in I band is going off. So the 2011 AA in the luminosity decline rate, assuming a Hubble parameter of 72. This is the data from Hicken et al. And overplotted with the Phillips relation and position of 2011 A, which doesn't really an outlier, but it still shows spectroscopic diversity and also photometric diversity. So it is the slowest declining type 1a supernova, and no secondary maximum has been observed in I band, and its spectral evolution is not very similar to superchandra or either normal 1s, and we have shown it to be the explosion from a violent merger of white dwarfs. So so thank you all, and this work has been submitted in the Astrophysical Journal, and we are working on the company. Thanks.
All right, thank you for this talk. Any questions about this slow declining supernova?
So Anirban, from some of the other talks in Boom this past week, we've heard from folks like Melissa Graham that binary white dwarfs, because of binary population synthesis, must be the majority. We've seen that there's no hydrogen in some of these things, even looking at really late time. But if binary white dwarf systems are supposed to explain the majority of type 1a supernovae, and here you're positing that they explain an extremely unusual event, what strictly makes the binary white dwarf model different for this object? You had said violent, but is it purely the kinetic energy of the system that's different? Is there any polarization data to tell us if there's any understanding of binary for this object?
Yeah, so it's a wonderful question. So so the polarization observations of a superchandra object in 2009 DC showed that it showed no polarization. So from there, it is like they're saying that I don't know how to constrain it from polarization. These are all asymmetric in nature, these explosions like violent mergers and all, but like presence of oxygen in the inner layers has been for a supernova 2010 LP in the nebular phase. So nebular phase observations are very crucial for finding whether they're violent mergers or collisions. Collisions will show bimodality in the nebular phase, like bimodal or two peaks in the nebular phase spectrum. And if you observe violent mergers, it has been shown that they show nebular oxygen 1 in their nebular spectrum. So nebular spectroscopy should be more of a more useful thing to observe, and also polarization data should be very important, so because these are all asymmetric, and so some kind of asymmetry should be there. Yeah.
We have time for one succinct question and response from Peter.
All right, so I'm just interested in the excess UV luminosity of this object. Have you looked into whether that's consistent with these violent merger models?
Not really.
That is in fact succinct. Thank you so much, Anirban.